Alright, well, hello everyone. I am Mr. Santos, and we are here to talk about Atmel Studio 7, which is the primary tool that we will be using for the remainder of the semester. So let me just give it some introduction and motivation and who the audience is for this particular video. So in the past, in our course CEEN 1060, we have used for the longest time, or we have hung on to AVR Studio 4. Okay, and the reason that we did so was because the development kits that we use in-house in our labs use the At90 USB 1286 microcontroller. Okay, and this device was supported by way of a simulator in AVR Studio 4. Now, the simulator is very important because it allows you to step through your program in software line by line in your code, and you can analyze and understand what your code is doing before you actually upload the code to the actual board and run it. Yes, having hardware is very useful, but what the hardware does is that it only tells you whether your program works or it doesn't work, and you don't get to see what is happening line by line and helping you to understand basically how a microcontroller program executes code and how does the code changes the state of the microcontroller and a variety of its peripherals. You will not understand that without having access to the simulator, to the excellent simulator that was in AVR Studio 4. Since then, Atmel has moved on to a version 5, 6, and now their latest version is 7, which is what you're seeing here right now with no project presently open. Okay, since this semester we changed our labs, we upgraded all our computer systems, and that means we also upgraded our software, and I believe the version that we have installed in the labs is 6.1, but it's very similar to version 7, which I have here. And also, if you choose to download, and I highly recommend that you do so, download Atmel Studio on your own for your own machine, it will most likely be 7. So therefore, I choose to give my demonstration using version 7 of Atmel Studio. Okay, so this is a video, is sort of a tutorial for my students. If you are not a student and you happen to you're watching this video, please note that it is given in lecture format. So if you're looking for a quick show me how to do this, how to do that, you're not going to find that in this video. So this is targeted for a particular lab for my students. So let's go ahead and get started. So we have the problem that I've stated previously. We have, let me just kind of give you a quick overview, draw some stuff here. So when you write code, we're going to be using the Atmel At90. It's called the AT90 USB 1286, okay, which is an 8-bit microcontroller. And these are part of our deb kits, which we just call the blue boards because the boards are blue, okay, or BB for short. Okay, but in Atmel Studio, all right, there's no simulator support for this device. We can write code for it. We can upload the code into the blue board and run it, but we have no way to actually simulate and understand and check our code as we build up. Therefore, we're going to do our temporary solution for now is that we're going to write our programs targeted for the Atmega 324p. Right, this device in Atmel Studio 7 has simulator support, and therefore what we're going to do is that we're going to set up a solution. That is a term that is part of the Microsoft Visual Studio IDE, in which Atmel Studio is built upon. Right, and inside of our solution, we're going to set up 2 projects. One project we'll call the target, and another project will be for simulation purposes. Right, since these 2 devices have very similar, almost exact architecture, we'll be able to write code for the Atmega 324. We'll be able to simulate it, test it, debug it, be certain as much as we can through the simulator that our code works, and then after that, we're going to retarget it for the At90 USB 1286, and then we'll run it on the actual hardware. So we'll simulate on this device, and we will run it on the target hardware for this device. Okay, so we will set up a solution in Atmel Studio 7 that contains 2 projects, okay, set up accordingly. All right. So that's basically the general principle of how we're going to solve our little dilemma of not having access to a simulator for the actual device that we'll be using in class. Okay. Generally, the way it works is that you will write an assembly program, which is just a text file with the extension ASM, and this all happens inside of Visual Studio or Atmel Studio 7. All right. And then once you have written your code, you will go ahead and you will build it in the code. Typically, this means that your ASM file will run through an assembler, AVR assembler, and it will generate an object file, .obj, containing the object code. Okay. Then, in addition, there's some additional tools that happens. This all happens behind the scenes. The object file will be used to generate what is called a hex file, an Intel hex file containing the actual ASCII representation of the code. Okay, so this is an ASCII, a special ASCII format of this object code. This hex file is basically what we want in the end. This is the end of the endeavor. So you work, maybe 4 hours or 4 days to work with this. You build and you simulate, right? So maybe you'll do some simulation to test your work over and over, and you edit your code to fix things, and you keep this cycle going. And then when you are done, right, you generate the object code and the hex file. The hex file is basically what you upload from the PC onto the board. So you have your blue board, okay, connected to your PC running Atmel Studio 7 via USB cable, all right? And once you have generated a hex file, this is the file that you actually upload to the blue board. You run the blue board, and then you determine whether your program works or not. All right. So this is basically the general approach that we will be using. But again, normally that only requires 1 project, but because we don't have a simulator support, we have to set up this 2-project approach into a solution in Atmel Studio 7. And I will show you that here in a minute. So let's just go ahead and get started on that. So obviously, the first things you're going to need to do is you're going to need to download Atmel Studio. Of course, we have MML Labs also. Okay, but just so that I can show you, you go to atmel.com. All right, then go to, this might change by the time you view the video, but I believe it's under support. Go down to Atmel Studio IDE. And then scroll to the bottom, and you have 2 options. You can download the web installer, which is 2.39 megabytes, and then once you run that web installer, the web installer will go ahead and proceed with downloading the actual Atmel Studio to your machine. All right, and note that the installation overall time is going to be very large. It's about 1 gigabyte. All right, or you can download the offline installer. All right, and it's going to be that big. But then you don't need web access to do so. That's up to you how you want to do it. Just understand that because the Visual Studio program is fairly hefty, it will take at least 30 to 45 minutes to install, regardless of how fast your computer is. And that's just the way it is, unfortunately, because it's such a big program. Okay. All right. So once you install that, let's go ahead. So you have installed it. Let me go ahead and restart this from the beginning so you can see. So you have Atmel Studio 7. You double click on that, and then we wait for it to start up. Okay, and it will usually take you to the start page, and there's just some announcements if you're connected to the web. This is not important. You can dismiss the start page. All right, there's just an empty page. So what we're going to do is we're going to set up a solution containing 2 projects. One for the AT90 1286, which will be our target. Okay. And one for Atmega 324P, which we'll use specifically for simulation. All right, so let's go ahead and we start by going to File, New, Project, and under Install Applications, we're going to go ahead and select Atmel Studio, and we have a blank solution. Okay, now let's pretend this is our first lab, which is Lab 2, where you will be doing we'll start using the simulator. So let's say Lab 2 Solution. All right, make sure that Create Directory is checked. You should always have that checked. make sure that you're aware where in your directory you're saving your solution, because you will be looking for some stuff inside of these folders, and I will show you later. Click OK. And we have nothing really much happening. We have a blank solution. We look at the Solution Explorer. It shows you everything that is part of our solution, and we have a solution, but we have nothing in it. So we'll go ahead and select that, which is already selected, and right-click. Move this over. Right-click, Add, New Project. Okay, under Install, we want to go for Assembler, AVR Assembler Project. All right. And our first application will be a Lab 2, and we'll call it Simulator. Okay, so this is the project for running our simulator. We click OK. We select the device for the simulator. So we'll go for Atmel 324P. If you look at the device info on the right and we scroll down here, it'll show you why we want this. It has simulator support. Okay, click OK. And now we have an empty project. If we look at the Solution Explorer, we have our project simulator, and we have our one file associated with our project, which is the assembly file. If you double click on it, this is the assembly file that we have here. Okay. Before we do anything with this, let's continue to set up the project. So we select again now the project, not the solution, the project. Right click, Properties. Okay, we're going to select the properties. Alright, configuration. We want to set this to all configurations. We want to affect both the debug and the release. When you're working with your project, you can have different settings for debug or release, but we're not going to do that. We're just going to have the same settings for debug and release. Okay, under device here, we want to make sure that the device is indeed Atmel 324. If you incorrectly chose you chose the incorrect part, you can click on Change Device and select it. Okay, that's good. Under Tool, we want to select Debugger, Programmer, and select Simulator. That means we want to be able to use the simulator, the integrated simulator, to simulate our software, to debug our software. All right. And lastly, under Tool Chain, this is very important. Under General, make sure that you uncheck Generate Hex. This is a safety feature. We want to make sure that we use this exclusively for the simulator, and we do not want to accidentally generate the hex file, because what I see happening is that many students will generate a hex file and they will end up uploading the wrong hex file to the target device. They will not match. Okay, we don't want that to happen, so we turn that off. Okay, notice that there's an asterisk here next to the solution name. All right, I mean to the project name, saying that we need to save. So Control S to save, and that will save our project options. So this is set up to go. Okay, let's go ahead and now add the target project. So once again, we select Solution, right click, New, add New Project, Assembler, and we'll call it Lab 2 Target. All right, this is the part of the program of the project that will generate the hex to run in our target device, which is the AT90 1286. That is the device that we use in this course. Click OK, and we have target device all set up. Okay, there's nothing to do here for project properties. All right, we'll leave everything as its default. All right, we are going to generate the hex, the map file, and the list file. And of course, you want to verify on the device that it is indeed AT90 USB 1286. And if that's not the case, change the device. Okay. Under Tool, notice that we do not have an option for simulator. So that's the reason why we have to set up a two-project solution. And so that's all there is here. Really, we did nothing. So Control S to save that and dismiss the window. Okay. Now let's go back to the simulator. So you need to double click. You need to be careful. Notice that it's the same source code, default source code here, and I cannot tell which is which. So it's always important to always look at your Solution Explorer and instead click here and here so that you know what you're working with. So let's start with the simulator. Alright, all of our code must have, delete everything, all of our code must have author. Okay, so in my case, my name, but make sure you include your partner or partners' names into your source code. Okay, maybe date. Alright, so let's say August 29, 2016. Lab number. Okay, so let's say lab 2 activity 1. Usually our labs have multiple activities, and then a short brief description of each activity. So program for activity 1, intro to simulator. Always put that. So all your programs must have what I call a comment header. That means a header with some basic information of what this program does. Now let me just start typing some stuff in here, and then we'll go back to explaining what each of these are. So, most basic program. So this is our simulator. So M324 pdef.inc. Okay, org 0. Let me just say $0. Okay. My first instruction is to jump to the start. Place data here. Start. Let's add some code. LDI R16. Let's say 1. And LDI R17. Let's say 10. Well, let's specify that in hex. And I'm going to add R17 with R16. Alright, and let's go ahead just for fun. Let's increment after that R16 for no reason. And after that, let's put an infinite loop. Okay. We'll add a label called forever, and then we'll do a jump to forever over and over again. And lastly, we want to tell the assembler that there's no more code to look for, so let's just put an exit directive. Okay, now let's just go ahead and talk about what's going on here. On the top, first line, dot include. That is a directive. Anything started with a dot means a directive to the assembler. A directive is an instruction that instructs the assembler to do something. It does not translate into code. Therefore, I'm actually instructing the assembler. Right? In this case, the dot include directive takes the contents of this file called that, and it places it in this file as if I had typed the entire content onto my program here. Okay. The .org directive basically specifies what is the beginning address for any subsequent code. So all of my code starting from this line will start at address 0, and I will show you what that means later when I show you the list file. Okay. So because Atmel microcontrollers, when you reset, they start at address 0, we want to have some valid instruction at address 0. And therefore, my first instruction is to do a relative jump to a location called start. Where is start? Well, you define that location by adding a label. Right? A label is basically a literal string that ends with a colon. I do this on purpose because in future labs, I will actually place some data in here. And I do not want that data to be interpreted as instruction or code. Therefore, to prevent the microcontroller from executing that code, I jump over that data and proceed on to where the code begins. Alternatively, you can place data where it is unreachable down here after the infinite loop. Okay, that's your choice, but that's normally my style. Alright, then we have some instructions. So LDI means load immediate into R16 the value 1. Okay, so this translates into R16 gets placed the value 1. Load immediate R17, register R17 gets the contents 10, which is written here in hexadecimal. A $sign indicates that the number is in hexadecimal format. If you don't have a $sign, it is interpreted as decimal. Then I want to add the contents of 17 and 16, and I will put the result in 17. So whatever is in 17 will be lost. So 17 will be replaced with the sum of 17 and 16. Okay, and then for fun, I increment by 1. So what this is going to do is this R16 is going to take in whatever its value is, plus 1. And then we have the infinite loop. So what is the purpose of the infinite loop? Well, later in the future, we will place procedures. So all procedures go here. We don't have procedures here, but in the future they will be there. If you don't have an infinite loop, what's going to happen is that your code is going to execute line by line, and it will run into the procedures. Procedures only get executed when they're called by you. They should not be accidentally run into by the microcontroller. So an infinite loop prevents us from runaway code. It also ensures that your program is still in control of the microcontroller, and it also keeps the microcontroller in an alerted state so that it can always respond, for example, to external events such as external change interrupts on the external pins, etc., etc. Okay, so this is very common in embedded system software. Okay, so I am done in here. All right, and now I want to simulate this code line by line. I want to make sure, I want to see what it does. I want to understand what it does. And that's what the simulator is for. Okay, so in order to do that, all we have to do is you either go up here. Well, first we got to build it. Okay, remember I said in our little diagram that I have pulled up here is that after you have written your assembly program, you want to build it. Then you can simulate it. All right, so let's do that. To build it, you go up here, build. Now, if we do this here, this will actually build both projects, the simulator project and the target project. I don't really want to do that. You can. There's really no harm in it, right? But instead, I just want to build my simulator. So what you do is that you select the project, you right-click, and you build it. And you're going to get some message here in the bottom. The thing that you're looking for is that the build succeeded. And number 1, you want to see if you have any errors or warnings. If you have any errors or warnings, you should really try to understand what is the source of those errors and those warnings. Okay. You also get some basic statistical information such as how big your program code was and whether you use any data memory and whether you use any EEPROM memory. Okay. You can dismiss this when you're done. Alright, we're successfully built, so therefore we can go ahead and begin debugging or simulating. You want to do that by clicking here on Start Debugging and Break. Or you can hit Alt F5 on your keyboard, or we can go on to Debug and go Start Debugging and Break. So let's just go ahead and do that. And so the debugger has started, and break means to pause in the first line. Okay, to pause on some designated line. And in this particular case, we're stopping in the first line. So here we're now in debugging is in effect. Alright. Notice that we have the yellow arrow. It points to the instruction that will be executed next, but has not yet been executed. So I have not yet executed my first line. Alright. Which is just jump here. So if I want to step through the code line by line and I want to run execute each line, there's basically 2 key commands you want to be aware of. And number 1 is that step into or F11 or step over F10. Let me just give a quick overview of what that means. If you have a program, an assembly program, line, 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 maybe you call a procedure. Let's call a procedure foo, line, 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 and let's call a procedure bar, line, line, line. Okay, and here's your infinite loop, so you can't get past it. And maybe right here you have a foo procedure, and let me just put it sideways here, a bar procedure with a return statement. The purpose of a procedure is that as you're running your code line by line, there may be several things that you do over and over again. Maybe you need to call foo several times. To do that, you don't type the code 5 times. Instead, you just call foo once, and then it does its thing, and then it comes back, and it continues. Then it calls a bar, then it does its thing, then it goes back, and it continues. Alright, that allows you to reuse code. When you are debugging, and you do step over by hitting F10 on your keyboard, okay, right? And you're debugging line by line by line. Then it gets to call foo. If you hit step over, okay, what's going to happen is that your simulator will go inside of foo. It will execute all instructions as fast as it can, and it will immediately return back, and it will stop here at the following line. Okay, this is useful, for example, if you have debugged your procedure and you are certain that it works exactly as you want it to, then you don't want to waste time by going inside and also stepping line by line by line by line. Instead, we step over the procedure. This is what that really means. Step over means step over procedure. The other one is step into. F11. Okay, in that case, if I was hitting F11, 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 then it goes inside F11, 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 and then when it's done, it will return back and it comes back here. But now I'm going inside line by line. So your choice whether you use step over or step into depends on whether you actually want to go inside line by line into the procedure or not. All right. Usually you choose step over until you actually have a need to step into. Okay, so that's the difference between step over and step into. So again, F10, F11. So I'm going to hit F10. All right, if I hit F10, it jumps to the next instruction. Okay, so it executed a jump to start, and it did so, and it went to the first instruction there. Okay, now I'm going to hit F10 again, and it's going to move 1 into R16. Now, there's something I want you to notice. On the right here, I have a window containing register values, and it shows me what the register file is. All right, the register file refers to basically a view of the contents of all the registers and what its values are. Right now, by default, they're reset to 0, but you should never assume in actual hardware that that is the case. Okay. But in this case, they're all zeros. So when I hit F10, R16 will be loaded with 1. So I hit F10, and lo and behold, notice that R16 changed from 0 to 1, and it changed red to let me know that there was a change there. So let's go back here. I hit F10 again. Now we have R17. It's loaded with A. So that's number 10 or 10. And then I'm going to add the 2, and I will replace R17 with the sum. So we go back here, press F10. And I have 11 in hexadecimal. Okay, then increment again, F10, R16. So R16 will change from 1 to 2. Hit F10, and lo and behold, R16 has changed from 1 to 2. Okay, so, and then lastly, we have the infinite loop. So if I keep hitting F10 over and over, it looks like it's doing nothing, but what it's actually doing is that it is jumping back to itself. It is an infinite loop. I got my program locked in here forever until I push the reset button. If I need to reset my program, look for the reset icon. 6.1 might have a slightly different icon. Alright, but just be aware of that. If I click reset, it goes back to the beginning, and I can resimulate my code again. Alright, now there's some things I need to make you aware of. Number one is the information that you see when you're debugging. If I'm not debugging, let me stop the debugger. I see my solution explorer, but I don't see anything else. So there's center information that you will not see until you're actually debugging. So let me start a debugger again. Alright, and I see registers here showing me the contents of the registers. I see the processor status, and I see my memory contents. If none of these windows are visible, let's say that I don't have registers. Okay, these icons here, right? So I have, let's go through each one. So when I'm debugging, I can look at a disassembly of my code. No disassembly available. Why is that? That makes no sense. Let's stop the source code here. Let's do another build. Let me start a debugger. Right, disassembly. There it is. Okay. So I can see my code is assembly. Now, since my code is already in assembly, it really makes no sense. Disassembly means that if you're looking you're working with high-level language like C or C++, then you want to see the actual assembly behind that high-level language. You can click on the disassembly to see how your code is being disassembled from high level to assembly. Alright, but just know that that's what it means. Next is the registers. So if I hit on registers, it will show me the contents of the register. Now I purposely put it over here. If it's not there, you can detach it. If I click, this window will attach, and you can hover your mouse wherever you want it and then let go, and it'll attach it, and you can resize it as however you see fit. Okay. After that, we have memory. So if you click on memory, we can see the contents of memory. All right. The AVR architecture has 3 memories. One is the flash, where your program code is stored. The other is data memory, which contains both registers. All of these registers are mapped into SRAM or static RAM. And we can see I/O memory. All the I/O registers that to control a variety of the peripherals in the device are also mapped to SRAM. And then EEPROM. In much later labs, we'll be working with EEPROM. All right, we can store. We can actually, if you click here, I can actually change the values by pushing on the keyboard. Okay, and I can actually simulate my EEPROM containing some preliminary information just for simulation purposes. Okay. If we look here on the right, let me put this back onto program memory. On the right, we have processor status. All right, we have the program counter points at the instruction that will be executed next. So the address of this line here shown in yellow is actually 00. Okay, my stack pointer, my XYZ pointer registers, we will learn about that in class. The status register contains 8 individual bits that shows you the state of the processor after executing certain instructions. Cycle counter, how many cycles have occurred for each instruction executed. The frequency, which is 1 megahertz, and that actually matches our actual blue board, which does run at 1 megahertz. The stopwatch, which tells you how much time has elapsed after each instruction. This is good for tuning software delays, and you will write software delays. And you can actually see registers also on this window, so I technically don't need this register window. You could actually see that information here. So I run my code. Let me hit F10 again. F10, F10, F10. And it does its thing. You can see that the address of the program counter is increasing. And you can see the cycle counter is increasing. And you can see that my first 4 instructions took a total of 4 microseconds to execute. And again, the same information here that is in here is also visible here. Okay, and then lastly is I/O. This is so that you can see the registers on your device. The microcontroller has many peripherals, for example, ports. And you can actually either encode or you can actually click here. So for example, suppose I want to read some data from my port, I can pretend that that data is sitting on my port by just toggling bits with my mouse by clicking bits on and off. Right? So this is a great way to simulate your device. Okay, so that is simulation. All right, let's stop the simulator. Okay, so suppose you're done with your program and you are certain that it works. You've done all the simulation you can. You're ready to move this into your target hardware. To do so, all we have to do is select everything, copy, go onto your target main, Control A, Control V to paste and overwrite everything. And we only have to change this one line, USB 1286 def. Okay, so this is the include file specifically for our target device. Once again, I want to build it. Once again, we want to ensure that we have a successful build and that there were no errors. If there are any errors or any warnings, you need to address those errors and those warnings. Alright, so what did I say? Let's go back in here. What is the output of the build? It's the object file and the hex file. So, remember I said you need to remember where you place your solution. For my system, I have my solution to here. And remember, you have simulator and your target. For your hardware, we're always going to the target. Notice that your assembly file is in here. You can actually view its contents. Okay, this is good for pasting into your report or just printing it directly from the text file itself. If you go into the debug, because we were in debug mode on our Atmel Studio 7, all the files will be placed in the debug folder. What's the file that we want the most? Hex file. Let's look inside. Our 3 little lines of code, this 3, 4, 5 lines of code translates into this hex file. Okay, so the utility that will be used called flip will basically understand how to take this information in the hex file and upload this into the blue board so that it's actually runnable. Okay, let's see what else we have here. We have a list file .lss, and this is many assemblers generate list files. List files shows you the actual content fully expanded. What do I mean by fully expanded? Let's go back to Atmel Studio 7. Remember I said the purpose of the include is to include whatever's inside of this file and put it in my file as if I had typed it entirely in here. Okay, my list file shows me the fully expanded content. So that include file contains all of this, and this is provided by Atmel. And if we look very closely, what we have is a whole bunch of equates directives. This allows me to refer to memory I/O addresses by way of just symbolic names. Instead of saying put something in 0x92, I can say put something in TCCR3C, right? And this is what makes code portable. This is what makes it possible for us to write software and simulate it in one device and easily move it over to the other device, right? Portable code. So this file, that include file, contains a lot of equates. And at the bottom, so it ends here, and this is our actual code right here. That's the code that we wrote. We have the org says I want the instructions hereafter to start at 0, and indeed they do. Notice that it starts at 0. Our jump start instruction is encoded as that. Okay, my LDI instruction is starting at address 1 is encoded as that. The next line is at address 2 and is encoded as that. The next line is at address 3 and it is encoded as that, etc., etc. Following that, there's some statistics. Basically, it just shows what registers were used in your program. Okay, it shows you what instructions were used in our program. We used the INC instruction, so therefore that counts as 1. Okay, we use the LDI instruction twice, so it shows me that. And memory usage, my code data, my executable or runnable code took very little, just like 12 bytes. Okay, and I have no data, and I have no EEPROM data assigned, so therefore all that stuff is completely available, and I have no errors and warnings. So this is very useful for trying to see exactly how your code, your assembly code, is expanding completely before it's actually consumed by the assembler to generate the object file. What else do we have here? A map file. We can view that also. And a map file basically contains a list of symbols, right? All of the symbols that are used in your code and what their actual numerical representations as addresses, what they translate into. Okay. But that's beyond the scope of this class, but just know that it is there. The object containing the executable. Alright, let me just show you what this will look like, and it's just a whole bunch of random stuff. You can't see it because it's just runnable object code. Okay, and this is just a temporary file generated by Atmel Studio, so we can ignore that. But again, the most important file is the hex file. Okay, let's get back to that. So we are done. So this is basically the general approach that we're going to have to use. In other words, let's summarize again. For each project, for each lab, we're going to create a solution, and each solution will have one target project and one simulator project. Now our labs actually contain multiple activities. So that means that for each activity, you will need to create a solution containing, again, a project for simulator and another project for the target. All right. Now, let's modify. We're going to do one more thing here. It's going to be tedious to have to redo all of these for each new project, for each new solution. Luckily, Atmel Studio, and as is Visual Studio, allows you to export a template, a project template. A project template is a ready-made project that contains all the settings in place, set up, so that you can just say new project, and boom, you can just go ahead and get started. So let me just show you what I mean by that. Okay, so I'm going to actually erase, well, not, we're going to keep some things. So I'm going to generalize this as a template. So author, I'm just going to put author question mark. And date, I'm going to put date question mark. On lab, I'm going to put lab question mark, activity question mark. And then for description, I'm going to say description question mark. I'm going to leave that there. I'm going to say jump start there. I'm going to leave my infinite loop there. I'm going to leave that there. I'm just going to make myself a note. I'm going to say your code here. Control S to save. I'm going to take this and I'm going to copy all of it, and I'm going to go into my target, and again I'm going to select all, paste, and again I want to make sure that the include file is the right one, so USB 1286 def inc, Control S. So save it. Okay, so I'm going to save this as a template, one for each project. Okay, so what I do is I go ahead and say file, export template, and let me make sure, so I'm on my target. Let me start with my simulator. So file, export template, project template for this specific project, simulator project. I click next. Let's just call it lab, let's just call it CEEN 1060 lab simulator template. Okay, and we want a short description. So let's say CEEN 1060 simulator project. Okay, and let's say add, to make ourselves a note, add mega 324p. Okay, I'm going to copy that. I'm going to use it again for my target. Okay, and then you can save that, and it will be saved as a zip file in a location indicated here. In addition, you can have it automatically import that into Visual Studio. So that means the next time it will already be added to Atmel Studio 7, and I can already select it. So I'm going to leave that selected, and I'm going to select Finish. And here is my list, my zip file. I can actually say that. I can put it in a thumb drive, and then maybe when you go into the lab, you can say File, Import, Project Template, and then you won't have to generate this template again from the beginning. Okay, I'm going to repeat again the same thing for my target. So, File, Export, Template, Project, and I don't want to select Simulator, I want to select Target. Okay, let me put that in here. Okay, and I want to make sure that this has the right information. So add 90 USB 1286, and we want to change it to Target Project. Okay, so CEEN 1060 Target Template. Okay, same deal. I want to automatically import it into Visual Studio. I'm going to hit Finish, and now there's my other target. Okay, and again, you can save these two onto your thumb drive, and you can import them in lab. But the idea is that you do this in your own machine. Okay, now let's see how this works. So suppose I have another activity that I need to work on, and I don't want to do this all over again. When you're done with your project, you can just go to File, Close, Solution. I will close both projects. And I want to start a new project. File, New, Project. Same deal though. We need an empty solution. Let's just call this Lab 2 Activity let's say that you have another activity, so activity 2 solution. Okay, click OK. I have an empty project, but now I can say File, Add, New Project, and if I go under Assembler, recent. Where are my? Where's my install template? I think I need to restart. Hold on. Let me exit. I may need to restart Atmel Studio 7 for it to catch up. Let's see. So let's open recent solution. Let's open project solution because I already saved one. So let's call it Lab 2 solution. Open. It's empty. So if I say right click, add, new project, assembler, there it is. Okay. So lab simulator. And you call it whatever you want. So again, Lab 2, Activity 2, Simulator, and it gets added. Notice that my template code is already there. Everything is set up. My device is set up. My simulator is already set up. I'm ready to go here. I can go back to Solution, Add New Project, Assembler, Target. So once again, Lab 2, Activity 2, Target. Click OK. Simulator target is in here, and my code is ready to go. So once again, the idea is that you go back to your simulator code, you add all the information in the comment header, you add all the necessary code. When you're done, you copy this, you select everything, paste it here, making sure that you maintain the right header file, and then you build it and you upload it onto your target device. Okay. Once again, the templates are also saved as zip files, right? When you created the template. So if you save this into your thumb drive and you go somewhere else, you can actually import the template and then reuse these templates. Okay, and I might actually post these on Blackboard for you to go ahead and use them right away. Okay, a few more things. Resources. Okay, in Blackboard. Nope, that's not it. Blackboard, all right, for my students. Remember that we have the data sheet containing everything you need to know about the AT90 USB 1286. Okay, as an engineer, you always have to look at and read the data sheets. So as we learn about new devices, okay, you usually want to look at the index. So for example, let's say we're going to learn about ports. One of the first things we're going to learn about is I/O ports. Let's see if I can find I/O ports. I/O ports. So you go to the I/O port chapter and you need to read about the I/O ports to understand how the I/O ports work. They're usually registers that you need to set up in order to use the I/O ports properly. So for example, port names. Continue to scroll down here. So for example, we have ports. We have each port has 3 registers: a port C register with 8 bits, data direction registers with 8 bits, and an input pins for reading data into the microcontroller. There are 8 bits, and these bits are described in detail in the documentation. What do the bits do, etc., etc. So anytime you need to learn about some interrupts, when we go to interrupt vectors, it shows you what the interrupt addresses are and what important registers might be and what the significance of each bit is. So you need to read documentation to understand how to properly program and use the microcontroller. Also, there is an assembler user guide. The assembler user guide tells you how to use the assembler. Remember, the assembler has a whole bunch of directives. Okay, so there is somewhere in here, there's a summary of the directives that are supported by the assembler, and here they are. Remember, we talked about the include directive and the .exit directive. If you want, and the org directive. If you want to find out what each of these means, you can read the documentation about the assembler to find out what it means. Lastly, the instruction set reference. You will not be able to understand how to create a solution if you don't know what instructions you have at your disposal. If you want to understand how add works, for example, once again, we look at the, add. It shows you, it gives you a mnemonic that the add takes a destination and a source register, and it puts the result in the destination register. Notice that the destination register might be any value between 0 and 31, and the source register any value between 0 and 31. Sometimes that's not the case. Sometimes that is the case. In any case, the instruction set tells you what instructions you can use and how each instruction works. So I always recommend that you always look at the instruction set reference and to try to learn every time a new instruction and to write some small program into the simulator so that you understand how the instruction works. Okay, that is imperative. Okay, so I think that I've covered pretty much everything that I thought it was really important for you to understand. Just a warning that many of the lab handouts make references to Atmel AVR Studio 4. That's what it used to be called. I need you to make sure that you know how to use Atmel Studio 7 and make a mental replacement of every instruction referring to AVR Studio 4 and replace that with Atmel Studio 7. Okay? Or 6. They're very similarly compatible, so you should have no problem. All right? Thank you for your time. I hope this video helps you. And if you have any questions for me, of course, you know my students, you know how to contact me. So, and in either case, I will see you in lab. All right? Thank you for your time.